Introducing EKAS, Exoskeletal Knee Augmentation System. We are a group of 5 students working together to design a lower leg exoskeleton meant to increase the functional range of human lifting power by providing support as the user does a simple squatting motion. The knee is one of the most complex joints in the human body and is especially prone to injury from high-impact activities or repeated stresses. For this project, we chose to focus on ways to provide strength and higher load-bearing capabilities to the knee while avoiding wear and tear on the joint. The final product consists of a lower leg brace, which uses motion sensors and a motion prediction algorithm to predict the user's movement, and then sends commands to the pneumatic actuation system, which then provides appropriate mechanical support for that motion. The project is aimed at helping already healthy factory workers who are at risk for knee injury due to the nature of their work, as opposed to current exoskeletal projects which target medical patients requiring rehabilitation. Because of this, the final product should be able to provide enough power to help the worker do their work more efficiently and effectively. We chose to limit the scope of this project to focus solely on providing the user support when they're picking up or lifting a weight. This allowed us to create a specific machine learning algorithm tailored to predict squatting and standing motions, and tailor a matching actuation system to match the expected loads. In order to narrow down and quantify particular specifications, we broke down our initial needs assessment into 2 parts, production side and user side. On the user side, we focused on making the product safe, durable, and affordable. As we mentioned earlier, we aim to design fail-safe mechanisms, redundancy, and an ergonomic, well-fitting brace to ensure this. We also specified that the brace should have a lifetime of at least 2 years and comply with an IP50 ingress protection standard to ensure it can be safely used in outdoor environments. We also aimed at having a lifetime of 2 years, or about 36,000 load cycles. Additionally, we aimed to make the device and production process relatively affordable. Specifically, we aimed for it to stay under $400, the given budget for this project. The needs from the production end are focused on the technical design aspects, processing speed, and load-bearing capabilities. We concluded that the total response time should be less than 8 milliseconds, which allows for 3 milliseconds for the device to intake and process motion sensor data, and then 5 milliseconds between the control signal reception and the motor actuation. In terms of load-bearing capabilities, we determined that a functional prototype should be able to output a minimum of 80 pounds of upwards additional force.
To obtain control and information about the user's knee position, we needed a platform that interfaced between the user's leg and the actuation and sensing system. This component must disperse highly concentrated stresses of the actuator along the user's leg to avoid injury. The structural elements of the system can be split into 3 main design elements: the hinge, the structural bars, and the straps. The hinge was designed to mimic the movement of the human knee joint as closely as possible. Spur gears at the end of each structural bar interlock in a 3D printed housing, which also holds an interior plate with rubber beams. Second, the structural bars. Made of aluminum 6061, the bars are designed to minimize stress concentrations and deflections due to the actuation force while remaining light and manufacturable. These parts interface with the straps, which serve to eliminate the difference in position between the user's knee and the structural bars.
To augment user power output, we use a pneumatic cylinder. At 29.9 psi, based on the geometry of the fake leg, the expected vertical force output at the hip was approximately 50 pounds. Restriction on the testing meant that we were unable to verify this calculation. The pneumatic system for controlling the piston consisted of a ball valve, a pressure regulator, an air filter, a 3-way 5-port normally closed solenoid valve, and 2 adjustable flow control valves. During testing, the plan was to adjust the valves to match a median extension or contraction velocity, and then control speed by opening and closing the solenoid valve. The intrinsic compliance of the pneumatic system can dampen sudden stops and starts to create a more continuous velocity distribution. To control the actuators, our device uses a network of several sensors placed along the brace. We use a combination of 2 LS-M6DS3 6-degree of freedom IMUs and 1 BendLabs digital flex sensor to read the angular position, acceleration, and orientation at 3 separate points on the leg. This data is fed into the Adafruit Huzzah 32 feather, which pre-processes the data to remove invalid readings. From here, the data is sent over Wi-Fi using the OSC protocol. While originally designed for use with audio equipment, OSC allows us to easily and efficiently send numerical data through UDP packets with minimal losses. The components communicate with the central controller using I2C protocol. We considered sourcing sensors that use analog outputs instead, but we determined that for the small additional cost, the greatly decreased software and system complexity of the I2C boards was worth the cost. The software system was developed in order to convert the readings pulled in from the sensor system and convert them into commands for actuating the piston. In order to collect data, we had a user squat and move with the brace and classify when it should be actuating or not. This allowed us to perform supervised machine learning to predict when the user wants motion. Typically, the data is already collected and then applied statically. In this case, the data was collected on an initial prototype and was used simply as a proof of concept. Going into the initial data collection, we knew that we would have to run the machine learning software on a new dataset. This strategy still showed basic trends within the set and allowed the team to optimize hyperparameters and begin feature engineering. This allowed us more time to develop the model throughout the year rather than doing the bulk of the coding and data analysis on the final brace model. The final model used AdaBoost, which is based off of random forest. We were unable to collect data on the final motion prototype. Nevertheless, we were able to achieve an accuracy of 98% in the sensor to actuator model using the early prototype's data. This indicates that the final product would have functioned as intended. We hoped with this project to make an exoskeletal design that could provide the same functionality as existing designs at a fraction of the cost. This would make the design far more accessible for mass production and widespread use for various applications. While we likely would have exceeded our initial budget of $400, we predict that the initial prototype would have remained below $500, and thus well below similar exoskeleton projects. By keeping the cost significantly below the current market price for similar exoskeletons, we can also potentially lower the functional cost for large companies by replacing larger machines and helping laborers do manual work at a faster rate. By extending the scope of the project to include other types of motion, we could also expand into other applications. To expand the design even further, we would recommend first exploring ways to validate ethical testing methods to verify it is comfortable and functional for everyday use. While we can test the brace fit and load-bearing capabilities using a testing jig, it would be beneficial to study how the brace feels on an actual person. We could also look into adapting the design to support other types of motion, such as walking or climbing stairs. This would include adapting our algorithm to recognize different sorts of motion, or including some sort of switch or dial to allow the user to manually indicate the change. It may also require adaptations to the actuation system, especially for periodic movements like climbing stairs. As the academic term was shortened, we weren't able to complete a fully integrated prototype. However, we were able to finalize physical prototypes of the necessary electrical hardware and an early model of the machine learning algorithm. While we couldn't complete a physical brace or an actuation system prototype, we were able to model these systems in CAD software, estimate a bill of materials, and virtually design a testing jig.